In this video, we are going to see about the slip power recovery scheme applicable to slip ring induction motor. So in that, we will see about static Kramer drive. A slip ring induction motor consists of three-phase winding at its stator and the rotor windings at one end they are connected in star, and the other end are connected to the three slip rings to which brushes are connected, and from the brushes you can connect the external resistors. The speed of a slip ring induction motor can be varied by controlling the rotor circuit resistance. Basically, there are two types to control the speed of the slip ring induction motor. One is the rotor resistance control. Another one is called slip power recovery scheme. In rotor resistance control, we are changing the rotor resistance and controlling the speed of the slip ring induction motor. Basically, the slip power is wasted in the resistance in rotor resistance control. In slip power recovery scheme, as the name suggests, the slip power is recovered here. So what is done? The slip power, instead of wasting in resistor, it is returned back to the supply. So there are two techniques to achieve this slip power recovery process. So that is called Kramer system and Serbius system. This Kramer system or Kramer drive will operate in subsynchronous speed, whereas Serbius drive can operate in both subsynchronous as well as supersynchronous speed. So in this video, we will see about the Kramer system. Already we have seen about the rotor resistance control in the previous video. I will give the link in the description. If you want to check it, you can go and click the link in description. In slip power recovery system, the slip power is returned back to the supply. So what is slip power? In induction motor, we have air gap power. A part of the air gap power will be converted into mechanical power, and the remaining power we call it as a slip power. So this slip power can be returned back to the supply. So how to return it? We have three-phase AC which has a supply frequency. Say I am having 50 Hz supply. This slip frequency will be different from the supply frequency, because slip frequency is S times the supply frequency. So this is a different value. So I cannot directly connect this slip power into the supply line. So first I have to convert this into supply frequency. So for that, what I can do is convert this into DC. So using a diode bridge rectifier, I can convert this into AC to DC. Again from DC it is converted into AC of supply frequency. So I can match the voltage and frequency and connect it to the supply again. This slip power can also be used to drive another motor connected to the main motor. So in that case we call it as slip power is the feedback is mechanical. If you give the slip power to the AC line directly, we call it as electrical feedback. So it can be used to drive another motor, or it can be returned to the supply. So by utilizing this slip power, our overall efficiency of the system can be improved. Now we will see about the static Kramer drive system. So here we have a three-phase AC supply connected to the stator winding. From the rotor you are getting the slip power. So this slip power is converted into AC into DC by this diode bridge rectifier, which will have some output ripple will be there, which can be filtered out by this inductor. Then this DC is again converted to AC by the line commutated inverter, and this AC output, which will be equal to the supply frequency, will be connected to the three-phase supply using a transformer. We call it as a line commutated inverter because natural commutation occurs in this thyristor inverter. So in static Kramer drive, we can see that the slip power can flow only in one direction. That is, it flows from the rotor circuit to the supply only. So one direction is only allowed because we have a diode bridge rectifier. This is also called constant torque drive because we are returning the supply slip power to the supply. And here in static Kramer drive, we can achieve speed control only below synchronous speed. Now let us derive the torque equation and draw the speed torque characteristics. So first let us start with voltage equation. This derivation will be similar to the rotor resistance control. So whatever steps we have followed, we will follow the same steps. So the V1 is the stator voltage per phase, and SE2 is the rotor voltage, and we have this turns ratio. A is equal to rotor turns per phase divided by stator turns per phase, which is given by N2 by N1. So the stator voltage when referred to rotor circuit is equal to A times SV1, which is also equal to S times E2. So this is given as input to the diode bridge rectifier. Now we will write the diode bridge rectifier equation. So for a three-phase diode bridge rectifier, the rectifier output voltage is given by 3√3 VPM by pi, or VPM is nothing but √2 times VRMS value. VRMS is the rotor voltage we have already calculated, that is AS1, ASV1. So if you simplify, you will get this one. So simplify it, VD is equal to 2.339 SAV1. So far we have calculated the output voltage of diode bridge rectifier. Till this part we have completed. Now let us come to the next part, that is the line commutated inverter. So we have to calculate what will be this voltage VDC. So a rectifier, when it will act as a inverter, when alpha is greater than 90 degree, it can act as an inverter. So this is basically a phase control rectifier. When we make alpha greater than 90 degree, it acts as a line commutated inverter. There are two cases. We have seen that we use a transformer here to connect it to the AC supply. So first we will derive the equation without transformer, and then we will see what happens if we connect a transformer and do the calculation. So this average DC output voltage without any transformer, VDC is equal to, this is a phase control rectifier direct equation, 3√6 divided by pi V1 into cos alpha. Here negative sign indicates that it is inversion operation, or this alpha is greater than 90 degree. So we will get VDC is equal to minus 2.339 V1 cos alpha. First we are assuming that there is no load in the circuit. So when there is no load, torque is 0, or this current, rectified current, DC current is 0. So if this current is 0, this voltage and this voltage remains the same. So VD we have already calculated, VDC also calculated. If ID is 0, this voltage is equal to this voltage. So equate it, simplify it. If we simplify it, you will get the slip value as S is equal to minus 1 by A cos alpha. So here we have not considered the transformer. Suppose this A is equal to 1. What is A? It is the rotor turns ratio divided by rotor turns divided by stator turns. So if that is equal to 1, S will be equal to minus cos alpha. So if alpha equal to 90 degree, slip is 0. Slip is 0 means you will get synchronous speed, because slip is ns minus n divided by ns. So you are getting 0 means machine is running at synchronous speed. For alpha equal to 180 degree, slip will be equal to 1. It means that it is a 0 speed. So as we vary the alpha from 180 to 90 degree, the no load speed is controlled from 0 to synchronous speed. So while doing the slip calculation, we assume that A is equal to 1. That is the rotor to stator turns ratio is 1. Actually it will be less than 1, because this is stator voltage, whereas this rotor voltage will be less than the stator voltage, because rotor voltage depends upon the slip. Slip value varies between 0 and 1. So always rotor circuit voltage will be less than the stator voltage. So here you get only stator voltage. So this stator voltage cannot be directly connected to the supply. You have to match this voltage and this voltage. For that you need a transformer here. So we are including this transformer and doing the calculations again. So AT is the turns ratio of this transformer, that is the per phase input voltage to inverter V2 divided by per phase supply voltage V1. So here V2, V1 is specified. So now we have included this three-phase transformer. So what will be this VDC output? It will be equal to minus 2.339. Simply multiply by the turns ratio AT V1 cos alpha. Same equation, only you are including one AT, because you are considering this turns ratio also. Now again let us equate these two, VD and VDC. So simplify it and get slip value. So slip also just multiply by AT, you will get the slip equation. So S is equal to minus AT by A into cos alpha. Next we will calculate the torque equation. So the total slip power is 3 times SPG, that is equal to output power VDC into ID. So this PG is the air gap power, which have PM divided by 1 minus S. And this PM is omega m into Tm, and omega m is 1 minus S into omega S. So we can write this, you can simplify this one and find what is the torque Tm. Now we are getting the torque without transformer and with transformer. So first for VDC we will substitute the voltage equation without considering the transformer. So it is equal to minus 2.339 V1 cos alpha, and S is equal to minus 1 by A cos alpha. Let us substitute this one and get the torque equation. So you got one torque equation which is proportional to the A, the turns ratio A, V1, ID, and inversely proportional to synchronous speed. Now let us consider the transformer and derive it. So when you consider the transformer, you will get AT in the voltage equation, as well as in slip equation you will get one AT. but this is in numerator, this is in denominator. So both At will get cancelled and again you will get the same torque equation. So we can observe that the torque equation remains the same irrespective of we connect the transformer or not, or it is independent of the transformer's turns ratio. So torque is directly proportional to the DC link current, supply voltage, this rotor to stator turns ratio, and inversely proportional to the synchronous speed. Now let us calculate the DC link current. So initially we assume that there is no load and this current is 0. But if we load the system, current will flow, so that torque will develop in the system. So ID is given by VD minus VDC divided by this particular resistance of the coil. So VD minus VDC divided by RD. So we can calculate VD from here. But what is VD? This one. So let us substitute this and you can find what is the slip from this one. Now again we can substitute the value for VDC. So what is VDC? This one. Substitute here, simplify it, you will get the slip equation. So we know motor speed is equal to 1 minus S into omega S. So we have calculated S, substitute it, you will get the motor speed. So we have calculated the torque equation Tm. So let us include the load torque also. Now when under steady state, the total torque is given by 3 times Tm. So this TL represents the load torque, that is equal to 3 times the motor torque. That is equal to Tm is this one. So this 3 and this 3 get cancelled. So you are getting load torque. From that you can find what is ID. This ID you substitute in the motor speed equation and get the equation for motor speed. So you can see that the speed depends upon AT by A ratio, AT by A into cos alpha minus K into load torque. Let us see the speed torque characteristics. So this is drawn for different firing angles. So alpha equal to 90 degree to 180, we are drawing the speed torque characteristics. So this characteristics will be similar to the separately excited DC motor with armature control. So here also we can achieve speed control only below synchronous speed, and within only narrow range you can achieve speed control. So this has a limited application, like it is basically used for large pump and compressor drives. This is a diagram of a closed loop control for static Kramer system. So as I told earlier, the power circuit remains the same. You keep the power circuit as such, and now what you can do is, outer you have speed control loop and inner you should have current control loop. So here measure the speed, give the reference speed, it will calculate the error, give it to some controller like PI controller, which will give you the reference current. Then you measure the actual current and give it to the current controller, which will give you the gate pulse for the inverter. So this is a diode bridge rectifier, so there is no need for firing pulse. So the advantages are, they are preferred in large pumps and compressor type drive where range of speed variation is very limited, and this drive is efficient. And converter power rating is low because it has to handle only the slip power, because slip power is less than the supply power. So slip power converter rating can be less. And the control circuit is also very simple. If you see the disadvantages, it has a poor input power factor. And the rectification process, that is you are using power electronic converters, will introduce harmonics in the rotor side which will be reflected in the stator side. So and you have increased machine losses due to the harmonics. So the points to remember here are the slip power recovery scheme can be achieved either by Kramer drive or Serbius drive. So in Kramer system, slip power can flow only in one direction, that is from rotor circuit to the supply, and it is called a constant torque drive system, and we can achieve speed control only below synchronous speed. If you like the material, do subscribe to Read Electric Vehicle channel. Thank you.